Go ahead. Thank you. So today I would like to tell you about a description for the physics of scattering amplitude, which has as its starting point not finding diagrams or Lagrangian or fields, but rather a geometrical object defined by some notion of positivity. So these objects, these positive geometries, live in some space which, to begin with, can you read like this? Okay. In some space which may or may not be immediately regulated with the kinematical space of some theory. So the space of variables in which we decide to, in terms of which we decide to write the amplitudes. We are really just defining some auxiliary space where we consider some functions whose positivity carve out a region which is our positive geometry. From the positive geometry, we can obtain the amplitude by asking some appropriate question, which may be computing some differential form or computing an integral over the positive geometry. Without going too much into the details of what is the question that we ask to this object and which spits out the amplitude, the reason we have a hope that this could be possible is because the positive geometry has a boundary structure which is able to reproduce the singularity structure of the amplitude. For instance, at tree level, a scattering amplitude can only have singularities when a subset of the external legs carry a total momentum which goes on shell. And the residue on that pole, that singularity is a simple pole, and the residue on the pole factorizing into the product of lower point amplitudes. For each such factorization channel, the positive geometry will have a boundary, which of course is obtained when sum of the function becomes 0. And that boundary is itself a positive geometry because some function is set to 0, but then we have still the other functions which are non-zero and carve out a region. And that boundary, which is itself a positive geometry, will have to factorize in the same way as the amplitude factorize. That is, it factorizes into a simpler version of the positive geometry. And these are really the positive geometries that we would use to compute the factors of the amplitude. Okay. Of course, we can go further and further, so we can try to further factorize this amplitude, and it means that then we explore further boundaries of the original geometry. Now, I don't want to give the wrong impression that this is a completely systematic way to compute any amplitude of any theory in terms of some question asked on some positive geometry. We really have a few examples where we see this precisely this picture working. Historically, the first one was planar and equal force superior Mills, where the relevant positive geometry is the amplitude-hedron, which was discovered by Nima and Jaroslav Trinka here in the Institute. Today, we are going to see a somewhat complementary example where we will consider a theory whose Lagrangian is maximally simple. Essentially, it's a colored version of phi to the cube theory, where each field carries two indices in a fundamental, let's say, UN representation. The interaction Lagrangian is going to be trace of phi cube. And therefore, as we are very familiar from Tuft, in order to organize the perturbative series of the scattering amplitude, it's convenient to use a double line notation, where we replace each field line with a double line, representing the two color indices. Therefore, every Feynman diagram is itself replaced by a flattened version of the diagram, which we can also think of as a surface. In this case, that is for market points. But for each diagram, there is a corresponding surface. Again, as we are very familiar from the one from the Lagrangian expansion, the basic building blocks which we need to compute amplitudes are really sort of colored amplitude associated to any given surface. Essentially, these are functions that depend on the moment of the external particles. They do not carry a dependence on the color. This is why they are called color ordered. And as you can imagine, they are given by a sum over all those diagrams, was a flattened version produces the given surface. So just to give a concrete example, literally from this surface, we would have two diagrams, which are an S channel and a T channel, which once flattened give this. Now, note that for this correspondence with surfaces,
the U channel is not there.
No, because the surface is orientable, so the orientation of the marker points is important. Note that through this correspondence, the propagators becomes dual to lines that you can draw on the surface, which have endpoints on the boundary of the surface. So this would be one line, and this would be the other. Okay, so because of this, we can really think of associating to every curve on the surface a propagator. So to begin with a momenta and then a propagator. Let's say that we keep our internal mass in the propagators. And because the external, well, of course, the momenta is just obtained by solving momentum conservation, but on the surface, it's really just a question of computing the homology of the curve. Since the external momenta only appear in the amplitude through the propagators, we can really think that this function that we associated to every given curve are really the function on which the amplitude depends. So we can write any amplitude as a function of the variables associated to the homology of the curve. And of course, propagators are essentially the singularities of the amplitude at 3 levels. Loop level have the singularities of the integral. And therefore, going through this correspondence, we would expect on the other side to find a geometry which will have boundaries labeled by curves on the surface. So let me think of this. So we're looking for some geometry which will have boundaries. So in particular, it will be given by some positive functions. And this positive function will be labeled by curves on the surface. That when 2 curves intersect, the corresponding propagator cannot appear simultaneously in a final direct. That means that these are singularities which cannot happen simultaneously in the amplitude. So in particular, it would mean that if you go on a boundary corresponding to this factorization, then you cannot go on a boundary which correspond to, I mean, essentially I'm saying that the boundary that corresponds to a factorization in the S channel cannot meet the boundary that corresponds to a factorization in the T channel, because these are not multiple singularities of the amplitude. So we want to keep apart the boundaries that correspond to crossing curves. And the simple way to do that, well, a very simple way to do that is by asking this function to satisfy identities among them of the following form. That is, we ask UL plus the product over all the curves that intersect a certain number of times L to be equal to 1. Now, from this equation, intersecting them with the positive region, it's clear why the geometry that emerges has these combinatorics.
Are UL and U minus L inverses?
Sorry?
If you reverse the orientation of L, do you exchange UL with its inverse? I'm just asking why there's a sign in the exponent here.
Oh, there is no sign. This is, sorry, this is the number of...
Just the number of points, not the intersection number.
No, literally the geometric intersection number. Yeah. So if we have two curves that intersect, then this equation will look like let's say that they intersect once, it look like this. And it's clear that I cannot send them simultaneously. Even more, if the functions are positive, but they have to satisfy this identity, it follows that they have to be between 0 and 1, because the sum of the positive numbers have to be 1. Therefore, if UL is going to 0, we really see that UL prime is going to 1. Because we have this behavior where things either goes to 0 or 1, we call this a binary geometry. And furthermore,
we call it what geometry?
We call them binary geometry just because it's made of these zeros and ones. And because it's a geometry which we attach to surfaces, we also call it a surface heater, a binary surface heater. proceed. Okay. Furthermore, what happens if we go to a boundary? So when we set one of these variables to 0, well, we are still left with all the u's associated to the other curves. So we have said that certain u's will simply go to 1, but others remain, and they keep satisfying this sort of equation. Only now the equation will simplify because many variables here will go to 1. So in other words, just to give a concrete example, if we were to do it at 5 points, and let's say that we set this variable to 0, then this variable disappears, but we're still left with these two variables, which keep satisfying this simplified set of equation without the crossing curves. In other words, we're writing the same set of equation that we would write on a simpler surface. The surface where this orange line has been pinched for a point. So this is why we see that this geometry has precisely this factorizing property that mimics the factorizing of the amplitude. Okay. So now we've seen both sides of this correspondence, and now we have to understand, I have to explain you how one can actually compute amplitudes from the geometry. What we will do is that we're going to integrate over the geometry a certain differential form. There is really not much to be said about this differential form. It's simply the differential form which are simple poles at the boundary of the geometry. But then this integral by itself would diverge, because it's like if you wanted to integrate dy where y and y equals 0. So of course it makes no sense. But as Euler did, you can regularize this integral by adding y with some generic power. Then this becomes 1 over x. And it's a perfectly well-defined function. Now, the analogues of this regulator in our case are going to be given by the variables which define the boundaries. So we're going to add a product over all the curves, and we're going to raise them to the kinematics, so to the value that we to the value of the propagator that we associate to a given curve. So we get a function of x and this common parameter alpha prime, which we can hope is going to be the amplitude. Now, as alpha prime goes to 0, essentially the integral would like to diverge, and the regions that are going to give you the divergences are the region where the u are going to 0, precisely as in this case.
Did you tell us what omega is?
Omega is just a differential form which has a simple poles at the boundary of the geometry.
It's not just the product of du over u, it's something more complicated.
Essentially, yeah, it's more complicated, but essentially it's something like that.
It's close to du over u 1 minus u, because it has to have singularities both as u goes to 0 and 1.
So, and then I guess that there are, in general, crazy numerators to make things work.
But is it uniquely determined?
It's uniquely determined by that. In fact, when I will tell you how to solve this equation in terms of certain variables, the differential form will be very trivial to write down. It's not where the magic is. So we were saying that this integral, as alpha prime goes to 0, sorts of localizes on the corners of this geometry, and the corner where you can set as many u's to 0 as possible. Because crossing things cannot be set to 0, you're essentially trying to set to 0 well, a maximal collection of non-intersecting curves. And through the usual correspondence between curves and propagator, essentially all these corners of the space are labeled by Feynman diagrams. So this looks, in the alpha prime goes to 0 limit, a sum of all the Feynman diagrams that give you the color of the graph of the value, so 1 over product of x. So as alpha prime goes to 0, this is definitely the trace of IQ amplitude that we wanted. And again, you can see that the reason why this formula works is because everything in this object factorizes precisely like the amplitude. Because I already said that this happens for the geometry itself. It also happens for the canonical form in a kind of a trivial way. In a non-trivial way, it happens for this regulator, because when you go to a boundary, we said that the non-compatible variable will go to 1. So you can imagine that here there will be the u that is going to 0, and you forget about it. Then there are all the U's that are going to 1, and they simply disappear out of the game. So you're left with the regulator that you would associate to a simpler surface. So also the regulator is, is factorizing. Now I mention it because the reason why these are called the surface hydra is because there are linear versions of these objects, just cut by linear equalities, and there the same game wouldn't work because linear function cannot simply go to 0 or 1 in incompatible boundaries. So this is why we really need this curvy version of the object. Okay, but then because this factorization doesn't really depend on alpha prime going to 0, you may wonder whether this is actually an amplitude even at finite alpha prime. But now you cannot get away with the problem of actually solving this equation. It's not enough to know what is the asymptotic behavior at the boundaries. You really need to look at this integral. Well, in the simplest example, we can do it immediately because we have only two variables, they intersect, so they satisfy UL plus UL prime equal 1. So one is U and the other is 1 minus U. So this integral is du 1 minus U from 0 to 1. So this is the differential form times U to S plus M squared 1 minus U T plus M squared. So if you set M squared to 1 to cancel this, you get the Veneziano amplitude. So it works. And it is amplified. Okay. So what we now want to do is to understand how to solve these equations in general on a generic surface and see whether we still find an interesting amplitudes.
Joe, maybe before you go on, maybe it's worth giving a tiny more intuition for what these U's are doing. As the U's are going to zip.
I'm going to do it.
Oh, you're going to say it. Okay.
So, but just a stupid question, maybe before you go on. But this way of regulating your integral, you do it by analogy, or is there a deeper reason to regulate this way rather than with some other way?
Well, I would say that the simplest reason why you consider these is to generalize the beta function, the definition of the beta function. And yeah, surely there are other ways to regularize, but I don't know if somebody has tried to see whether they also give amplitudes. Probably him knows about it.
Is the claim going to be that you produce other string amplitudes this way too?
I'm going to produce bosonic string amplitudes, at least in the simplest examples. But in fact, as you see, nothing in this argument depends on M squared being 1. So I'm really saying that these are an interesting class of functions that look like amplitude, and in the corner of all the possible choices, they are exactly bosonic string theory.
But yeah, okay, but I mean, you already showed it in one of the simplest cases, but I mean, how general, I mean, are you going to get the genus 0 endpoint functions that way?
Up to the genus 1, and if I have time, I will also say how we expect the situation to generalize to other surfaces. Okay, so to sum up, to begin with, we have to solve the U equation, and this is the first thing I'm going to discuss. Once we have solved them, we can look at this integral. And as we have just said, we know that on one direction, as alpha prime goes to 0, this integral is going to give us trace of I cube theory. In fact, to get trace of I cube theory, you don't really have to look at the full complicated nonlinear integral. There is a way to bypass it, and just from the solution of the U equation, obtain trace of I cube theory. The idea is that because the U's are positive and the space is positive, so you can parameterize whatever variable you choose to use to parameterize as exponential of alpha t, essentially, and you want to send alpha to 0. Well, then the integral is going to be the integral of an entire space, so the space of t's, and something like u to alpha x is going to turn into exponential of alpha log of u. Well, now the u are written in this way, and alpha is going to then you really have to compute this limit, the limit of the logarithm of the u's. And because the U's are positive, there is a simple way to do it without actually doing it. So it's a process called tropicalization of a positive function. Essentially, if you want to compute such a limit for a function like, let's say, x plus y times z, so a function which is written only in terms of pluses, minuses, ratios, but no minuses, then you can compute this limit simply by replacing plus with max. and times with plus. So this function tropicalized to that. So you don't really have to do anything. You just look at the U's, you tropicalize them as I just said. You get some piecewise linear function, and this integral gives you trace by cube theory. Because the integral is piecewise linear, if you want to do some further progress in computing this integral, you really have to break it up in the domains of linearity of this piecewise linear function. And it turns out that all of these domains are essentially in correspondence with the boundaries, with the corners of the binary geometry, and therefore are in correspondence with the Feynman diagrams themselves. So you discover that this integral, because it becomes a sum over Feynman diagrams, each cone is labeled by a Feynman diagram, and in each cone the integral becomes directly the Feynman parameterization of that integral. But this is something that it has context, because you start with an integral which is written in terms of well, essentially polynomially many variables, and the way they tropicalize, they create factorially many Feynman diagrams. Just to bring this point home, if you want to be brutal about it, if you just want to compute it, you put it on a computer, you compute it Monte Carlo by Monte Carlo iteration, and you get the amplitude without having to do a factorial amount of work. The story also generalizes at loop level, so you can always do the loop integral. It's always a Gaussian integral. There are no problems. So you really get the entire amplitude by doing a single integral.
So what is tropicalization supposed to do for you?
It turns.
I understand mechanically what tropicalization is, but what do you learn about the integral by tropicalizing it?
Well, you learn how to. You learn that all the diagrams really fit together in a unique integral, I would say, and I mean it's.
You're claiming that the tropicalization of your integrand is the sum of all the Feynman numbers?
Yes, because this is a piecewise linear function, and it's a matter of. Well, it's a matter of actually looking at the domains of linearity. But even if you have, it's the usual thing that you can have a polytope with a certain number of facets, but the number of vertices can be vastly different. So like here on the disk with market points, we have like n squared possible factorization channel, but factorial in many diagrams. So this is how factorial power, like a power number of things turns into a factorial number of things. But you can do it, as I said, by Monte Carlo, let's say.
I'm confused. Is there a misprint? Did you mean u equals e to the alpha t? You were integrating over the u's. And x's were external variables.
I guess it should be really a different parameter beta that controls how close you get to the. Let me put it about this as well.
So you're taking a limit of beta, but you're in. I don't understand. You're integrating over dt.
As alpha goes to 0, but essentially. You want to extract the leading singularity of this integral, and you know that the leading singularity is at the boundaries. So you want to write coordinates that allow you to get to the boundary, to the vertices. And the good coordinates are not the axis, but the log. So maybe a bit.
Sorry, but aren't you integrating over u? Or
sorry?
It looks like there's a typo on the blackboard where it doesn't make sense.
I am a bit confused right now. Ignore it. It's not a big deal. It's just a very standard thing that if you want to compute the leading order of such an integral, you have to compute these other integrals.
But maybe we can say that as the u's are going to 0, the boundaries of the u's going to 0. So since the u's are positive, right, u is e to the minus alpha. So u going to 0 is alpha going to infinity. And you can think of the alphas in the limit as the u's goes to 0. So those alphas are going to infinity. You can think of those alphas as the lengths of the corresponding, the Schwinger parameter, or the lengths of the corresponding world. So that's why the corners in which a bunch of u's are going to 0, this integral, and the integral has logarithmic singularities. So it looks like du over u, so it looks like integral d alpha, e to the minus alpha something. So that's why the kind of u integrals, the integral of this form with logarithmic singularities in the corners as the u's go to 0 looks exactly like the Schwinger parametric form of the corresponding function.
Yeah. The thing I'm a bit confused by is just that these alphas are not the same as alpha prime. Yeah. Poor choice of letters. Anyway, so at finite, but this is unfortunately, even though it's very exciting, is not what I'm going to tell you about today. I'm going to tell you about the finite alpha prime integral. And again, we're going to see that for a specific, by making some choices, such as m squared equal 1, essentially, we will find Bosonic string theory. Bosonic string theory. But okay, really, the first thing we have to do is to understand how to solve the equation.
You can m squared equal to -1.
It's let's not get there because it's really a bit a matter of convention. If I use specifically if I say that XL is 1/2 of what is written there, then I should put this equal to 2 and p square equal to 2. And then
When it's an amplitude, you should put m squared equal to -1.
if I did the thing I said there, here I would find here I would have these, and then I would have to put m squared to 2.
Minus.
Using all mostly plus.
I'm using this. No, it's like this. So you cancel these and you find
Well, I think m squared is not what's usually called mass squared. That's what's confusing us. The goal is that s plus m squared equals 0, which is s equals minus m squared. Oh,
Yeah.
Your s is minus the usual s,
I'm using the mostly plus. I'm using
but your s is minus the energy squared.
no, the s is the square of the moment associated with that moment.
So for a particle with time-like momentum, your s is negative.
Yes.
Yes.
So I think your s has the opposite sign.
Okay. And could be that I've done a small typo, but okay, let's not focus too much on this because it's.
So are you saying that the moduli space of points on the boundary of a disk is a cluster variety of A type?
This is it's one way to say, but I think I'm saying something a bit more intricate than that. Okay, so there is a cluster structure associated not to the modular space, but to the type modular space. So I just wanted to show you a specific example of these U equations written down for a simple surface, just to show you how they look like. When the surface is a disk with 5 marker points, we can label all the possible U's by the 2 endpoints. So we label boundary segments by some numbers. If we have 5, these are the 5 U equations that you have. And you can try to solve them in many ways. One way to solve them is just by solving them. So writing 3 of the U's in terms of other 2 U's, and you find something like this. You can try to generalize this strategy for any disk, but I don't know how to do it for any generic surface. Otherwise, you can be smart and realize that these U's can be solved, this U equation can be solved by introducing auxiliary parameters. And we know at least 2 different ways to do that. One way is using essentially hyperbolic geometry. This is related to the question that was just asked. Here is an example of the solution that we will find. And then there is a completely alien solution, which involves something called quiver representation theory, where the U's are written again as something like a cross ratio, but of polynomials which counts a representation. So something very, very different. Okay. So now we will see how the solution works. So we will focus on the second solution using hyperbolic geometry. And again, we will start from the simplest surface. So if the surface is a disk with marker points, we can redraw it as an upper half plane. And every curve that we can draw in the disk selects for us 4 points. So we also select 4 points here, A, B, C, D. And we set U to be a cross ratio that you can build out of these 4 points. The cross ratio that you get by pushing the curve in one way and in the other, this gives the denominator, so BD AC. Yes, sorry. Or in the other way, so you get AD, BC. Okay, cross ratios satisfies identity among them. There is one identity which involves 4 points. So this configuration. And you can imagine drawing this angle, this quadrilateral. And the identity says that the cross ratio of this curve plus the cross ratio of this curve is equal to 1. So u plus u prime equals 1. The other identity involves 5 points. So you imagine introducing a further point x in between C and D. And you have that this u is equal to the product of these u's. The u's, the cross ratios, telescopes. Now it's clear why we get the u equation, because if you want to compute 1 minus this u, it's going for 1 minus this u. It's going to give us the cross ratio corresponding to this other curve. But then we can telescope by considering all points that we have on one side and on the other. So this u becomes the product of all possible u that go from one side to the other. So we get u plus the product of u prime equal 1. Of course, here we don't have geometric intersection numbers other than 1, because we're like this. Okay, so our idea would be to try and use the same strategy for every surface. And we can try to do it using the fact that every surface admits as a universal covering space the upper half plane, which means that we can realize, at least topologically, every surface by quotienting the upper half plane by a group isomorphic to the fundamental group of the surface. But of course, because we use cross ratios, we would like this group to preserve cross ratios. So we would really like to use not any group of diffeomorphism acting on H, but really a subgroup of SL2R. These type of subgroups, isomorphic to the fundamental group of the surface, are called Fuchsian groups. Now, suppose that we have such a group, and without worrying too much what we actually get for the moment. So I will give a concrete example again. So let's focus on.
So we're discussing a surface that has any number of boundaries, including 0.
Yes.
In the setup surface.
Yeah. Essentially, yes. Well, we will really think actually that there are no punctures to begin with, so only boundaries, and but yeah, other than this, there is no restriction. Of course, we will exclude precisely those cases which are not hyperbolic. So we will not consider the sphere or the sphere with up to 2 punctures, the torus or the complex plane itself. But those are the surfaces that we care for the connection with trace of IQ. Okay, so let's consider this surface to begin with. The analysis with 1 marked point per boundary. Then it's easy to find such a representation of the fundamental group, because the fundamental group is just a Z. And an example of these subgroups of SL2R is simply matrices which rescale by doing this action, so scaling. Okay, so the covering picture will look like this. We will have 2 fixed points at 0 and infinity. And the lines that join them is essentially the lift of a closed loop on the atoms. On one side, we will have well, really every curve that you can draw, everything that you see on the surface, of course, will have a representative on the covering picture. So that the market points would be here, and now we will see infinitely many of them related by the Fuchsian group. And a curve that connects a boundary to the other boundary will look like this. But of course, a curve will lift to many, there will be infinitely many lifts of the curve. Because if you act by this SL2R, you get another copy of the same curve. Essentially, by acting, you're pushing this in this direction, let's say. Now, the U that we associate to a curve, of course, is going to be the cross ratio of the corresponding endpoints. And because there is an SL2R acting on them, the U that we associate to any copy of the curve are really the same. So just to continue to see how curves lifts. Suppose that now we want to consider a curve like this one. So connects the same boundaries, but once more. You get it by taking one endpoint and pushing it around the boundary. So for instance, you get it from this picture, from the original curve, by just doing the same. Okay. So just to complete the picture, we will also have curves that connect the same boundary. And here comes a surprise, because you can again choose how many steps you take in this direction. This corresponds to a curve that really self-intersects. This is something that I have not mentioned before. When we write this review equation, and in the moment we leave the disk, we are not able to find solution if we do not include also variables associated to the self-intersecting curves, which is a bit funny because they have no correspondence in terms of trace of IQ diagrams. Okay, so we will have this type of curves, and then of course the similar thing on the other side. Now it's the U equation, the proof of the U equation, it's essentially the same as the one in the disk. It's just a matter of realizing that many curves are actually the same up to identification. So we will have a gigantic U plus infinite product equal 1, but this infinite product will fold back into a product with exponents. Again, just to give an example, let's say that we want to look at how the U equation for this curve looks like. As we said, that these correspond to a curve like this one. If we take a further step in one direction, we get this curve. This picture. If we get a further step, so this curve goes here, and on the surface, it now corresponds to a curve that intersects the original one. On the upper half plane, they do not seem intersecting, but you have to recall that there are identifications. So this curve is equal to the curve that you get by pushing both endpoints towards 0. So it's equal to this curve. And now you see that they intersect. So this is telling you that this U plus this U times something else is equal to 1. If you do a further step, of course, you will find two curves that intersect the original one, and this is why the U of the more wound curve has an exponent of 2. Okay. So I've now
U plus an infinite product is 1.
U plus the infinite product with powers is 1. Yes. Okay, so now we have seen how to solve this U equation, but somehow I've hidden everything under the carpet because I've not told you how to actually produce this representation of the fundamental problem. This, of course, is a famous problem. The space of such a representation is called the tight-Muller space of the surface. And so in this way you think of the U equation, we really turn the problem of solving them into the problem of parameterizing this space. And then the U's, if you want, become functional on this space. There are many ways to parameterize it. I will just mention one particular way which is going to be relevant for us, and is by using so-called Penner coordinates, which are essentially lengths that you associate to curves that connect not boundaries but marked points. In this language, U become a ratio of lambda of this so-called lambda lengths. And the combinatorics behind this cross ratio is the same that I already used several times, and is to push the original curve in 4 different ways. So in the denominator, you will find the lambda lengths associated to these curves, and in the numerator, the lambda lengths of these curves. I'm mentioning this because in this picture, it also makes sense to associate a U variable to closed loops. Now, you see that the combinatorics behind how you go from how you write a U as if you want, how you factorize a U, is in terms of doing some simple operation on the underlying curve. The simple operation that you can do on a closed loop is adding a self-intersection. So you can imagine that above each loop, there is a tower of other curves. So there is that curve, and then there is this curve, and so on. And we will associate a U to each one of them by using the lambda lengths, which in this case are just the lengths of neighboring curves. Now, I agree with if you're if some of you want to complain about this, I agree with you that this is a kind of a ex machina formula. And the truth is that just using hyperbolic geometry, I don't really know how one would get to this formula. But recall that I told you that there is an entirely different way to solve the U equation in terms of something called quiver representation theory. In that theory, instead of seeing curves on a surface, you see an entirely different object, which is a representation of a quiver. There is, of course, a correspondence between curves and representation. And through that correspondence, there is really no difference between open curves or closed curves. They're really unified in a single notion. And there is a single formula that when you spell it out for closed or open curves, produces these two different formulae in terms of lengths.
Well, what's the definition of the lambda length? I thought the lambda length are only defined if the curve ends in the boundary of like a new line. Well, what's the meaning of the lambda length of the closed?
It's exponential of the length plus exponential of minus the length. And this satisfies the same
hyperbolic.
Sorry?
The length is the actual hyperbolic.
The actual hyperbolic. Maybe there is a 2 actually. And this still satisfies the Just one more thing that I wanted to say. Again, there is a beautiful theory behind the relation satisfied by these lambda lengths. And there is a famous factor related to a question that was asked before, that you can write all lambda lengths in terms of a minimal collection of lambda lengths, the lambda lengths that form a triangulation of the surface. And when you write the lambda lengths in those coordinates, you just get positive rational functions. So in particular, the U's will turn out to be positive rational function. And this, of course, is important for us because I told you that by tropicalizing them, we can compute just trace of vacuum. Okay, so
Positive rational functions means that both the numerator and denominator is a polynomial with only pluses.
exactly. Okay, now for the last part of the talk, I'm going to tell you how we see bosonic string amplitudes up to 1. So once again, we will start with the simplest surface, which is the disk. And as we said, we associate an integral over the space, the canonical form times the product. And as we said, for a disk, the product over all possible curves are leveled by the endpoints. So the product over uij of alpha xij. Now we can finally plug in our solution of the U's as a cross ratio. I will not write all the endpoints, but you know what they are. And when you write it like this, I will also write down the canonical form written in, ij are zi minus zj, and the z's are the position of the market points. So when you write it like this, well, the geometry is just all ordered points that you write down. TZ, the canonical form turns out to be this one. Recall that the x's are a propagator plus, a momentum squared plus an m squared. We can factor out the m squared, and depending on the precise convention that you use in defining the x's, if we say that x is half of p squared plus m squared, you would find the same factor, m squared arcs. And then we have to factor the u's, and the u's are factored in those simple polynomials, which of course get 4 x's. The combinatorics behind the x's is sort of the inverse of the combinatorics behind this ratio. So for each pair ij, you have 4 curves that contribute to that one. So they give you the x plus x, the x plus x, and the minus x minus x. And if you just compute these, sorry, I call them x, but now they are momenta squared. Here you will just find pi dot pj. So again, if you set m squared to 2, so that you cancel this becomes the the tachyonic endpoint open string amplitude. It's interesting to note that even if you didn't know about string amplitude, you would find that the choice m squared equal 2, it's a peculiar point in the space of all these possible choices, because it's where the integrand becomes permutation invariant. Because this part cancels that one, this is trivially permutation invariant, and you're really left with and this is perfect.
But isn't this the only consistent point? Because really this should be an n-3 dimension integral, right? Not a
Sorry, this is a this is a mod. Yeah, sorry, this is.
But
this
the
has
mod
to
is
be
only well defined precisely when m squared is equal to 2 or minus 2 or whatever it is. Otherwise, it's not well.
No, this is perfectly well defined for any m squared.
What after doing the mod, or I thought the mod as it
No, I mean, it sort of manifests in the original form. Everything is well defined on the surface. Omega is well defined on the surface. The uij's are all completely invariant. They're all SL2 invariant. So that's the point that Giulio is making. That's a sort of difference from the usual way we see the m squared, the constraint. Here, for every choice of m squared, you get something that's well defined on the surface. It's SL2 invariant. For every choice of m squared, it has a good field theory limit. But there is something special about the choice made in string theory, which is that only for that choice is the integrand, is this form actually permutation invariant. Why that matters is not super obvious, but it is a special point.
After all, I mean, you're writing.
Don't you have to divide by the modular group?
Apologies. Here there is a. Sorry, I forgot to write. There is a.
SL2.
Sorry, the volume. There is the HTC.
Nima, you're saying permutation invariant and not just cyclically invariant?
That's right. That's right. So it's so the whole thing. Yeah.
It's totally unclear why that's important physically, isn't it?
Yeah, it's just saying. I mean, we're really saying that there is a point which is more special than the others. We're not saying why that we should care about it. So if we didn't know.
But I think most of us don't know what the formula is when m squared doesn't have the usual value. When m squared has the usual value, you have SL2 invariance.
But after all, the integral starts its life as an integral for a space of cross ratios. So
I'm not questioning that what you're saying is true, but I don't know what the formula is when written in terms of Kobe-Nielsen variables. You can't get the Kobe-Nielsen formula for the wrong m squared because that would not be cyclically symmetric. I don't think. So you have to get something different. Okay.
It's not the Kobe-Nielsen formula. It's another formula. It's another cyclically invariant formula that has the correct field theory limit, et cetera.
That's what I said. It's not the Kobe-Nielsen. What I said was precisely, I don't know what the formula is for other m squareds, since it's not the Kobe-Nielsen formula.
Right. Yeah.
Sorry, the thing I should have said is that this is the formula, and when we set m squared to 2, we look at it and we realize the covariance.
So can you tell us anything when you don't set m squared to 2?
The truth is no. I don't know whether this function have something wrong with them. The only thing I know about this function is that they factorize in the correct way. They have the correct field theory limit, but I don't know if there is some other pathology which would exclude them.
But for example, Paul points that unitarity of the amplitude probably excludes some regions of m squared.
It's a range. It's an interesting range. So these amplitudes turn out to be unitary. So when m squared, when it's a tachyon, it's unitary and d equals 26. It's unitary and d equals 10 when it's massless. So it actually the critical dimension comes down as the mass gets bigger, and it stops being unitary when the mass squared is equal to plus 1/3, minus 1/3. So maybe something else goes wrong, but minimally the have to go up to m squared equals plus 1/3, minus 1/3 of this.
But it's very unclear to me. Are you reproducing the string amplitudes or not? Earlier, it was claimed that you were reproducing exactly the string amplitudes. From the discussion just now, it sounds like you're defining some other functions, not the usual string amplitudes.
Larger class of functions, which in particular give a corner of possible choice, the bosonic string amplitude, the tachyonic bosonic string amplitude. But we don't know what is beyond that particular choice.
They're all things that have decent field theory limit for any mass squared.
What we know about them is precisely what Nima just said. We know the field theory limit, We know that they factorize at least, well, they know that they factorize at finite alpha prime, and that's what we know. And then we know that they are.
The discussion of permutation symmetry and cyclic symmetry makes it sound like, you just said, is it or is it not equivalent to the Kobe-Nielsen formula? It's very unclear.
Equal to, yes, it's precisely literally the Kobe-Nielsen formula. This is literally Kobe-Nielsen.
I see. So a particular.
For a particular value of the mass, it's literally Kobe-Nielsen. For general value of the mass, it's something else. And it appears to at least pass the first physical consistency checks beyond the standard tachyon case. It works with something massive. It even works with something as massive, positive massive as +1/3 in these units. At least it passes the first physical consistency checks. But there is something special about why we care that it's permutation variant. It's not obvious why we care, but it is something special that happens. One reason you might care is, Giulio is not talking about it, but there's another way of making amplitudes like these, which is a sort of closed version, just the mod squared of these integrals. And then if you take this form and take the permutation variant version of it, you now get a closed thing, which is permutation variant, which is what you want for uncolored objects. So that's a reason to care about it. And also, if you sort of move away from the literal limit that he's talking about and start adding spin to some of the external states, you discover the same permutation and variance requirement says that something good happens when you have spin 1 particle that are massless and spin 2 particles that are massless and so on. So that mathematical fact about permutation and variance is doing some of the lifting that we normally associate with the consistency, the SL2 invariance of correlation functions of vertex operators.
Sorry, I'm going a little bit ahead because there was a formula that I wanted to write down before and then I didn't have the time. But so now I would like to move to the amplitude, to the integral that we would associate to this surface. And again, what I really want to show you today is how we get the usual bosonic amplitude that we associate to this surface. So I'm just writing it down for you. It's taken by Schwartz-Witten, 2nd volume. So incidentally, they use coordinates which are good for us as well. They parameterize the surface by going to the upper plane. So you will have a modular parameter W, which is the size of the annulus, and then you have market points on either boundary. So on one boundary I call them A, on the other I call them B. The formula looks like, I'm not going to precisely nail down every single detail because some of them are a bit tedious. I'm just going to show you the most striking facts. We have a product over all pairs of strings. When the pair of strings live on the same boundary, there is a. So we have an infinite product, and when they are on the same boundary, apologies, we have a minus sign. This is what I wanted to show you. And then there is an interesting exponential log rho A, the other rho A squared over log of that. Okay. If the strings are on opposite boundaries, the only difference is that here we have a minus sign. So let me write it like this. There are other important factors, but these are the most interesting ones to look at right now. Then outside of this, so this is a product over all possible pairs of strings. Then there is another infinite product outside of it, which doesn't depend on the kinematics. Is a sort of like it's similar to an eta function. It's called an Euler eta function, and it comes with an important 2 minus d, and then there is a logarithm of w 2 minus d times. Okay. Now let's see what we are going to have. On our surface, to begin with, there is now homology. I mean, now there is a loop moment in the game because there is some curve which cannot expanded by homology in terms of the external punctures. But it's not a big deal. We just have to integrate over the loop momenta. So curves like this one are carried. So connecting the 2 boundaries carry the loop momenta. And if you are more wound, so if you have something like this curve. Something that wind a number of times, the corresponding x is k plus, let's say that you wind n times, so k plus nq squared plus m squared. Q is the total momenta carried by the strings on either boundary. Okay, so we will have to do the loop integral, but it's not a difficult thing because when you expand this, forgetting for a second about m squared, you get k squared plus some linear term in Q plus some quadratic term in Q, which will carry this, we will have an n square index. So if you want to integrate d over dk, you're just dealing with a Gaussian integral because you will have to, when you factor the use, you will have to be careful about who gets the exponent k squared. So you will get something, and then you have to be careful about the linear terms. But you just do this integral by Gaussian integration. Nothing to worry about. So let's look at how the use factorize. I should write down for you the use. I didn't have time. So there are essentially two types of use corresponding to the two types of curves that we have. That will be real quick. If we consider curves that connect the two boundaries, say that here we have row A plus 1, and here we have row B and row B plus 1. Of course, the more you wound, the more powers of Wn you will have here. So if you compute the cross ratio, you find something. It's not important to look exactly at what we find, but really at the monomial the polynomial in which we factor. They look like row A, sorry, these are negative. If row are positive, those are negative. So we will have W row A, Wn row A minus minus row B. So things like this. And similar for the other three factors. It's convenient to write this as as 1 plus a something, so you can factor a row from each of the 4 factors, and they cancel. So in the end, you're left with polynomials that look like this. If instead you consider curves which land on the same boundary, it's the same story, only that we will have minus signs. Of course, these minus are related to these minuses. Okay. But then we can repeat the usual strategy. So we have the product over all possible lamination. Now, be careful, it's an infinite product because you have infinitely many winding variables. But even just the variables that go from a boundary to a boundary can be self-intersecting. So there are lots of infinite products, which you have to be careful in factorize. But the idea is always the same, that we have u as a ratio of 4 things, those 4 things. So you can, when you factor, you will have this x plus x minus x minus x that you recognize as a pi dot pj. So from this part of the computation, you're left with essentially this part of the GSW result. So the infinite product with these polynomials with either a plus or minus depending on where the strings to the pi dot pj. Okay. Then there is the loop integration. So schematically we get 1. Then there is the loop integration, and you have to be careful about who happens to be here. I will just tell you because there is not much time to do it. So you will have W and rho over W. Rho are the position of all the punctures. So you have something like this for each puncture. So when you do the Gaussian integration, this gives, let me write it here, you get log W minus d halves from the quadratic part. And then you get, so this would be, and then you also get, you write this as a log, so you get the log of rho squared divided log of W. So we get exponential. Apologies if this is a bit streamlined, but I don't have too much time. So these would be. So it looks like we get more or less everything, but we're left with a very important part, the eta function to 2 minus d. So like this, we don't get we're missing something. But after all, I told you to begin with that we were not, I mean, here I've been using only the use associated to the open curves. But I told you that there are also use that you can associate it to the closed loops. Unfortunately, I've erased the formula, but you have infinite many of them because you have use that, you have closed loop that self-intersect more and more. And it's not difficult to check that if you, well, essentially in the same way as this product of use to indices that raises quadratically, the product of those use, let me call them u delta j, product over j to the j squared, they give the product over n of 1 minus wn. So they give more or less the fourth factor that we are missing. However, there is absolutely nothing in our story to begin with that tells you what the overall exponent of this object should be. So it's like if we most naturally get that result where instead of having 2 minus d, we have some a. But now there is a nice argument, which is essentially, if you don't know about the string theory, but you got to this result and you think that this is an amplitude, this is historically how you can find that d is 26 and 2 minus d is 24. So not only you find that this exponent has to be 2 minus d, but you also find that the space-time dimension has to be 26. And it's essentially unitarity. You look at this amplitude and you realize that because of this exponential of 1 over log of w, this has a singularity around w equal 1. And that singularity, well, if you were to expand the integral being a bit careful, you would find that, let me call w, sorry, log of w, I'm going to call it delta. Around delta equals 0, it looks like, as I just said, it looks like this. Exponential of 1 over delta times q squared, where q is, as I said before, is the total momenta carried by one of the two boundaries. So, but sorry, more precisely, you also find, you still find, you find this w2 minus d when you expand around w equal 1. Now you can say you want to see how this integral, how this function looks like as a function of q. It's a good idea to call this quantity, sorry, as a function of big Q. So it's a good idea to call this quantity smaller q, expand around q equals 0, and you find that it looks like dq over q to q to some power 2 w survives to 2 minus d. So q and w are related in a very complicated way, and because here you have square. So if it wasn't for w, this integral around q equals 0, for the usual reason of the Euler beta function, gives you a simple Pauling q squared. So you can conclude that, sorry, here you find d minus 26. So you find that if d is 26, this part you don't have it, and you can conclude that the function has a simple pole. And then you can say, okay, then I'm just discovering that there is another particle and the amplitude has a pole in that particle, in that channel. If instead you do not have d equal 26, the function will have some branch cut of q squared, which breaks unitarity. You cannot understand that branch cut of quadratic. So you can repeat the same argument here. That, this a has to be minus 24 and the d has to be 26.
But you don't mind that m squared has the usual value?
In this computation, I assume that the m squared is actually as the actual value.
All right. Do you know if the annulus amplitude works well if it does not?
Unfortunately, no. I personally don't know. Maybe Nima, you know?
Sorry, what was the question? I didn't hear the question.
Edward is asking if we kept a generic mass, if we could still have essentially if we could still have a simple Pauling q squared.
Yeah.
I honestly don't remember. I would have to think about it. I don't know.
Well, it seems like it would shed light on whether your generalization really works. Would it not?
Sorry, can you say that again?
It seems it would shed light on whether your generalization really works.
Yes, I agree. Yes. I'm sorry, but I still don't.
There's actually a kind of a philosophical problem, which is that even for the Loveless argument, I mean, this is of course just the Loveless argument, but it's just the fact that there's a cut doesn't necessarily mean that this is something ill-defined. What you really have to check is that the cut it would be ill-defined if the cut had some wrong sign. Having a cut just means that we can't immediately interpret the discontinuity in terms of the amplitudes we've already defined, but it doesn't mean that it's physically consistent necessarily.
Well, you'd have to introduce new particles you don't know about. That you
Well,
might have
we did already. We did already here. We had to introduce a new particle we didn't know about. I mean, Lovelace did that. This closed string pole that of course is naturally there in the problem. So the fact that so there's a pole, so there's a new particle there, and you say you're happy there's a new particle and you discovered it. So yeah, it would be very nice if there was if there's a sharper problem with the sign of the discontinuity or something like that. But that's yeah, we're trying to figure out how to get that under control. But we don't know anything to say about that yet.
But in a similar vein, this also teaches you that you couldn't start with phi cubed UN theory, but that you have to start with non-orientable theory, right? Because you get the usual, like if you do this for the planar amplitude, and you get the usual pole, and you need to cancel it by the Mobius strip, and so it tells you that you also need like non-orientable diagrams, and like the way you started with UN, which has only the non-cross, like the double propagator with non-crossing lines. But you would also need the other one for this.
But I don't think that you need it for this amplitude. You need it for the amplitude where you have market points on your one bound, right?
Exactly, yeah, the planar one, yeah.
Singularity which is unregulated. So you can conclude that that's not a good surface to consider.
That won't work, I don't think, with unitarity.
Because you need this amplitude.
I would have thought so.
I mean, if you can't you just say that you do not associate an amplitude to this surface? Do you need an amplitude associated to this surface to guarantee unitarity for other amplitudes?
I would have thought so. Is
It
that right?
appears for even higher genus surfaces and particular degenerations, you would get this. So you would need to.
I don't think that I don't think you are able to degenerate a surface in such a way that you create an annulus with market points only on one boundary. Because if you let's try to think about it, but if you degenerate something, you would get. I mean, you can get this amplitude where you have a punch. Right? You can imagine that you have a boundary.
Well, I just thought of like starting with like genus 2, like a surface with 2 holes, and then you can like finish the cycle in between, and then you like.
Well, I was thinking the opposite.
know.
The annulus amplitude has a cut involving 2 of the particles you already had at tree level. And I would have assumed you need that cut.
Yeah, but it's these amplitudes. So these are the pole that you find in the non-planar amplitude is a product of the amplitudes that you associate to these surfaces. You don't need a hole, you need a puncture.
I thought you need the hole because it gives you the 2 open string cuts.
I think Giulio is interpreting what the closed string singularity is. Certainly, we need the annulus amplitude.
But he's saying that you could do without the case that all insertions are on the outer boundary. I'm surprised if that's true.
Okay, maybe I said something wrong. Maybe we cannot live without having also the annulus without market points. Sorry, with market points on your one thing. And then yes, I agree that you have to discuss also non-orientable surfaces. And that I cannot say much to be at the moment, because as you said, everything here was tied really to orientable surfaces. What I can tell on the moment, well, this is actually something that you mentioned to me, is that so to say, the modular space of the Mobius strip as a polytope, so to say, as a positive geometry, looks exactly like I mean, it has the same boundaries that you associate to this surface. So it looks like maybe there is also some way to talk about the modular space of non-orientable surfaces in the same language.
I'm confused by the discussion. You need the Mobius strip in a super version of the theory, which we're not doing now, right?
No, right now it's only the bosonic one.
So then you don't yet need the unorientable surfaces, I don't think, until you see
I think the whole point is that Lawrence was saying that here there is a singularity that can.
Yeah, the bosonic string, there's anyway a singularity. You can make it a little bit better by adding the Mobius strip, but you can't cancel it completely. It's just, like, I mean, there's a singularity that comes from the tadpole and screws you up in any case. Like if you would do this for a superstring, then they are.
We're not forced to talk about the Mobius strip for the bosonic string, but it's sick already. We can't prepare the thing.
Well, this is why we need to know if m squared can be positive. Because if m squared is a quarter or something, or negative in your setup, you wouldn't have a problem.
So I have a question. If I have a surface, perhaps with boundaries, but at least one marked point, and if I have boundaries, I have to mark points on the boundaries, then I can look at the SL2C Hitchin system on that surface, provided I put constraints on the conjugacy class of the holonomy around the punctures. And that SL2C Hitchin system has a cluster algebra structure. On the other hand, there's a real slice, which is the flat SL2R connections. And that has a component, which is Teichmuller space. So I guess that's a general argument why the Teichmuller spaces should have a cluster algebra structure. So my question is, has anybody tried to write standard string amplitudes in terms of cluster coordinates? Because the way I'm trying to understand what you're doing is you can take the string, you could, I guess, from what I just said, in principle, write the bosonic string measure in cluster coordinates, and then it might be a nice form which admits a generalization like your m squared.
Yeah, this is the content of the talk. I don't know if anybody tried before to write amplitudes in a complete fashion in terms of hyperbolic lengths, or as I said, in terms of cluster algebra.
This is really where the adventure began, Greg, was exactly this. The problem is that it's one thing to use cluster coordinates. That's fine. The cluster coordinates are a very nice way of talking about the Teichmuller space. The question is what you should be integrating. And it's not just cluster variables. That's all of these funny extra curves and so on are not simply cluster variables of the cluster algebra.
Well, I mean, they're coordinates, they're coordinates. So you can express any integrand in those coordinates. So I guess my question is whether the standard bosonic string integrand has a reasonably nice expression in the cluster coordinates. Maybe what you're telling me is the answer is
That's
no.
exactly what he's written down. Exactly. In fact, if you want to make it look more like cluster coordinates, you want to use the form that looked like the polynomials rather than the hyperbolic geometry looking way. And that form, those y's, you can really think of as very close to cluster variants. Yes, but the point is that to make these interesting U objects, these binary objects that are sort of built to make the field theory limit manifest, built to make the boundary structure manifest, and that using those functions raised to the exponents that are just given in the obvious way by the momentum of the curves on the surface is what gives you, that's what Giulio shown in the talk.
Well, they look very much like the variables that we associate to vector multiplets to wall crossing around a associated with a vector multiplet, where you have a product of an infinite number of cluster transformations. They're very reminiscent of that. I never thought of trying to make such a thing into an eta function, but it's certainly reminiscent.
Perhaps if I don't think I have them, but maybe if somebody is interested, I can say just one more thing to completely finish. And this is a simple argument why we expect that this is always going to be able to give us a bosonic string amplitude for more generic surfaces. And again, I will just streamline what the idea is. That roughly speaking, the string integrand is divided into two pieces. One is the part that depends on, it doesn't depend on the kinematics, and it comes from the Laplacian, from the determinant of the Laplacian on the surface. This was the thing that somehow is related to the closed loops. And in general, it can be written in terms of the Selberg zeta function, which is a generalization of the eta function. And Basically, it's something that is most naturally written in terms of length of closed loops. The formula for the Selbach zeta function is the same as this. Sorry, the same as this one. Is the product over all closed loops, and for each closed loop we have a further product. So the further product in our language is the number of self-intersection that you can add, and then you have this external product of the loops, of the different loops. So that would give the factor 4. All the other factors are essentially the green function. And if you write the u as a ratio of lambdas, sorry, of these lambda lengths, so these quantities that are associated to pair of points, when you write the lambda lengths in the upper half plane picture, they're really just the distances of 2 points. So when you do this factorization and you realize that x plus x minus x is pi.pj, you find something that looks like the method of images way you would use to compute the green function. Only that you're taking a product over, you're taking a product over a Fuchsian group, and it's not clear that the product makes sense, because after all, if you're not careful when you factorize it, if you factorize it not in terms of these polynomials, but in terms of these polynomials, the end factor is not even going to 1. If w is less than 1, this is going to row A. This is why I wrote it like this before breaking it up. So it's not clear how we can use the method of images to get the green function on a surface. It looks like the correct way to do it is to use the U. So the U's are giving the regularization for the method of images. And then this would explain somewhat more conceptually why you get the Bosonic Strings. Okay, now.
All right, so let's thank Giulio for the talk.